Hi there. In this video, we're going to relate confidence intervals and hypothesis testing and see how they relate to each other. So this is great because we get to see how they relate and we get to practice doing both some more. Okay, so instead of or in addition to doing a hypothesis test, we could take our sample statistic and form a 95% confidence interval. This would be similar to doing a two-tailed test at a 5% significance level. So even though we use different randomization distributions, right? We use a bootstrap versus a randomization distribution. They're both kind of looking at the middle 95% or the tails of 5%, right? So they're kind of similar to each other. So let's see how they relate to each other, okay? So, and we've talked about this too, but it's always good to repeat it again. The main difference in the simulation methods is the confidence interval is calculated with a bootstrap distribution, and then the hypothesis test is performed with a randomization simulation of the null hypothesis. Okay, so different distributions, but let's see how this works out. So let's look at an example. A national survey of 50,347 households in December of 2011 found that 30.4% of American households have a pet cat. And this was reported in 2012 in the Pet Ownership and Demographic Source Book by the American Veterinary Medical Association. Okay, very cool. So first thing we want to do is conduct a significance test to determine whether the sample data provide evidence that the population proportion of households who have a pet cat differs from 1/3. Okay, so this sounds like the claim to me, right? Determine whether, so that's test the claim that the population proportion of households who have a pet cat differs from 1/3. Okay, I'm going to circle that because remember, sometimes numbers can be written in words, so look out for that. We're going to state the hypotheses, report the p-value, and draw a conclusion in the context of this study. Okay, so let's do our significance test first, our hypothesis test first. And I've just got a blank sheet here. I don't have a distribution printed on here, so I'll do a little sketch when we get to that point. But let's write our hypotheses first. Okay, is it going to be a mean or a proportion, first of all? We're testing the population proportion, and that's what we're given, right? I'm going to underline this as well. This is our p hat, is the 30.4%, and the 50,347 is our n. Okay, so our null is that p is equal. Remember, the null's always equal. 0.304. I'll write it. Oh, sorry. That's our p hat. Silly me. Our p, hopefully you had already written 1/3. That's our null hypothesis, right? So we're testing that it's 1/3. So that's our null. Or, so I wrote it in a fraction, or we could write it as a decimal. Or p equals 0.3333. Okay, it's easy to get your p and p hat mixed up, so don't do that. Okay, then our alternate, that's our claim, right? That it differs from 1/3. So what symbol is that? And what type of test is this? Left tail, right tail, or two tail? So differs from would be not equal to 1/3. Or p is not equal to 0.3333. Okay, so if you said this is a two-tail test, you are correct. Okay, great. So yeah, it's just all blank here. So we're doing our test without the training wheels. Now we're going to go to our applet, right? So we're doing a hypothesis test. So that's our right column. Our bootstrap confidence intervals are in the middle column. The right column, we're doing a proportion. We have just one, not two. So we're doing a single proportion. And this is where we put in our p hat, right? That's, well, we can put in our null first. Our null is 0.3333. That's our null hypothesis. And I always check that that's, my scale at the bottom. That will end up being in the middle at the bottom. I always use that as a double check. And then we do have to know what size sample we're generating. So we have to put in our count and a sample size. Okay, so this is interesting. I don't know if you've run into this before, maybe, that we don't know the number. They gave us a percentage, but they didn't tell us the number. So we have to figure that one out, okay? So let's go ahead and do that. So let me get my calculator out here. If we know the total and we know the percentage, if we take that percentage of the total, we can find out how many households that was, right? So I'm going to go ahead and multiply by the decimal. So I'm going to take 50,347 times 0.304. Okay, and interesting, it's not a whole number, right? So this percentage was probably rounded. Okay, so it could have been 30.36% or 30.44%. So we're just going to estimate, and everything is an estimate anyway, right? Because we're using randomization. Everything's approximate anyway. So let me write down what I just did. 50,347 times 0.304 equals 15,305.488. Okay, now we can't put a decimal, nor would we really want to put a decimal into our app. So I'm just going to round whichever way. If this was 0.5, I'd round up. If it's 0.4, I'm round down. So 15,305. Okay, so we need that. In the case where they don't give us the numerator, we have to find the numerator ourselves or estimate it. Okay, so we've got 15,305 households out of 5,347. Okay, and when I hit OK, then I can double check that on the right, because our sample proportion should come out to what it said, what we were given, right? So we were given 30.4%, so that's good. That matches up. Okay, so those are the two things we need to edit to do our randomization distribution. Now, if you want, you can go right to 2000, or I can just do a couple here. So they're generating the same sample size using the 1/3 proportion. They got this many with cats. So you can see, and we've got null equals 0.333 down here, so it's going to vary around that. Go ahead and do 2000. It takes a second sometimes to do the 1000. Okay, great. So here's our randomization distribution. Assuming the null is true, assuming that 1/3 of households have a cat. And now remember, we were doing a two-tail test. So I'm going to click on two-tail. And then, so this is almost like, this is what happens when we do our confidence interval, right? The 0.95 comes up and we read these two numbers. But we're not doing that. We're not doing a confidence interval from this distribution. So we'll compare. But what we're going to do is we need to put in our observed statistic, the 30.4% of households. That was the sample statistic. A very large sample, but that was the statistic. And that's 0.304. So we need to put that in along the horizontal axis on the correct side. So if it's less than the null, we need to put it in the left side. If it's greater than the null, we need to put it in the right side. Otherwise it gets confused. So we need to put it on, in our case, it's below the null. So we need to put it on the left side. So I'm going to click on the left side, put 0.304. Okay. And now something kind of funny happened, didn't it? You may have noticed before that this distribution is really narrow. It goes from like 0.32, maybe 326 to 3.4. It's very narrow, because we learned that when we have larger sample sizes, the sample to sample variation is very small, right? So our standard error is 0.0021, so very tiny. So what happened when we put in our null value, when we put in our sample statistic, our observed statistic, it's way below the randomization distribution. So that never happened. It wasn't possible in our simulation for that to happen. The lowest was like 0.326 or something. I don't know exactly what that number is. Okay, so our p-value is 0, and that does happen sometimes. So I'm going to write that down. And then I'm going to draw a little sketch. Now, usually this graph looks more symmetric, but what they've done is they just try to get when it's a two-tail test, they try to get an equal area on the left and right tail. So the one that we didn't enter in, they just went to the end where it's 0. And so it's really, if I were going to draw it, I would make it symmetric on both sides. But they just kind of go out to the first time it's 0 on that side. Okay, so I'm going to just draw a little sketch of this. So our p-value is 0. So I'm going to draw, we had a very narrow distribution around 1/3. Oops, move this up. And then our value of 0.304 was way below that. So we had a p-value of 0 because on the left tail that didn't happen. So we had 0 in both tails. I'll kind of put the symmetric point over here. And then we had 1.0 in the middle of our graph. Okay. Okay, so to finish up our hypothesis test here, our p-value is less than, we didn't have a significance level, but let's use 0.05. So p-value equals 0, and of course that's less than 0.05. That's less than any positive number. So let's go ahead and write out our conclusion. With a p-value of 0, this is significant. We reject the null hypothesis. And I'm also going to talk about the strength of evidence. We have strong evidence, because we were just talking about that in another video. Very strong evidence that, and then I go back to my claim, the proportion of households who have a cat differs from 1/3. Oops, proportion of households who have a cat differs from 1/3. So 1/3 was not, if the null was true, we had no chance of getting the 30.4%. So we say that is that it's impossible under the null, or extremely unlikely under the null. So that's evidence for the alternate. Okay, so that is our hypothesis test. So that's a good review of that. Now we're going to do a 95% confidence interval for the population proportion of households who have a pet cat. Okay, so same quantity here, population proportion of households who have a pet cat, but this time we're going to do a confidence interval, and I've got a big blank thing here, so let's remember how we did that, right? Okay, so let's write out our sample statistic. Usually on this one, we would write our sample statistic, which we have above, is 0.304. Okay, and then we need to go into stat key. So let me go over there. So now for confidence intervals, we're in our middle column here. So which app would it be? Single proportion. Okay, and then in this one, we don't have a null that we need to put in. We go right to edit data. And this, again, we need our count. So we need that 15,305 out of 50,347. Okay, and remember this is a bootstrap sample, so this is going to simulate like we have 15,305 cat owners, like one colored piece of paper in a hat, and the rest are another color, right? And so when then we pretend like our population is many copies of that, and then we pull out 50,347 pieces of paper each time. We would never do this in real life. We pull out that many pieces of paper each time. Can you imagine trying to count those? And then count how many were cat owners. So that's what this is doing each time I generate one sample. It's 50,000 papers out of a hat, and count how many. Another sample, another sample, another sample. So this should be centered around our original sample, our original statistic of 0.304. We don't have a null hypothesis here. Okay, so I did a few, and it does, that's what it's doing. And I'm going to generate 1,000 and another 1,000. Okay, and then remember, for confidence interval, we always click two tail because we always need both bounds of our confidence interval, and the default is 95% confidence. So that shows up in the middle with 2.5 on each tail. So that is what we want this time. If we wanted a different confidence level, we would edit that. And then we look at our horizontal scale. And we read off our two numbers that separate the middle 95% from the edges. So we got 30 to 30.8%. Okay, so let me go ahead and write that interval down. Okay, put that on my paper. So we got 30 to 30.8%, and notice our 0.304 is right in the middle. It should be roughly symmetric, is right in the middle there. Okay, so we can write our conclusion from this, right? We can say we are 95% confident that the true proportion or population proportion of households who have a cat is between 0.30 and 0.308. Okay, it's also a very narrow interval. Did you notice that? It's very narrow because of our large sample size. Okay. Okay, so that's our hypothesis test. That's our confidence interval. Now let's compare the two, okay? Are the test decision and confidence interval consistent with each other? Explain how you can tell. Okay, so let me write the interval again right here so we can talk about it. So 0.30 and 0.308. Let's look at where the null falls there. So that's 0.30, 0.308. 0.333, if I imagine this on a number line, 0.333 would be way to the right, right? Correct? Okay, so it's outside. 0.333 is outside and way to the right of the interval. And that's our null value. So I could have said the null value. Let me put that up here somewhere. The null value in our null hypothesis is outside and way to the right of the interval. Okay, so if the null hypothesis is outside the interval, then that's what that's suggesting is it's not a plausible value for the true proportion, right? So let me write that down. The null value, so it's not a plausible value for the true proportion. Okay, so that's how we could conclude that, right? We could say the null's outside, therefore it's not a plausible value, therefore we reject the null hypothesis, right? So we reject does that match what we said with our hypothesis test? So I've got to move this down just a little bit for a second. So earlier we said with a p-value of 0, we reject the null hypothesis. We have very strong evidence that the proportion of households who have a cat differs from 1/3. So these match. Okay, in this case, they won't always match, but in this case they do match. So I'm going to write that. In this case, both methods give the same conclusion. And then I'm going to write, they won't always. Okay. Okay, so let's keep going. Got another page here. Have a couple more questions about this. Okay, do the sample data provide very strong evidence that the population proportion of households who own a pet cat is... Whoa, sorry, I got some problems with this. Hold on, let me pause this. I got some issues with this notes page. Okay, I'm back. I just had to reprint that page. It was too difficult, too wrong. Do the sample data provide very strong evidence that the population proportion of households who own a pet cat is different from 1/3? Explain whether the p-value or the confidence interval helps you decide. Okay, so we did find that, right? The sample data did provide very strong evidence. So yes, the observed statistic provided very strong evidence. Okay, but which one was that? Which method showed us that it was very strong evidence? That was the p-value, right? Bringing that page back down. So that was the p-value because it showed that there was 0 in all of our simulations. We never got a value as low as 0.304 or even really close to that, right? So the p-value gives us the strength. So hypothesis testing and the p-value tells us the strength of evidence. Okay, so let me write that down. The p-value in a hypothesis test tells us the strength of the evidence. Okay, that's the p-value. And then next question, do the sample data provide strong evidence that the population proportion of households who own a cat is very different than 1/3? So first we're saying very strong evidence. Now we're saying very different from 1/3. Explain whether the p-value or the confidence interval helps you decide. Okay, so again, I'm going to say yes. The observed statistic showed us population proportion is very different. Than 1/3, and which one was more useful in that, the p-value or the confidence interval? If you said confidence interval, that's what I'm thinking too, because the that tells us, that also gives us a width of the plausible values, okay? So the confidence interval, it tells us more about the size of the effect. How different is it from 1/3, okay? The confidence interval tells us about the size of the effect. And by that, I mean the width of the interval. Okay, we did see it a little bit from the hypothesis test as well, just because that 0.304 was so far away from the null. But we don't have a bound around that, so that's why the confidence interval is really helpful there. So that tells us by looking at the width of the interval, and then when we compare the two, it's whether the null is within or inside or outside the confidence interval. So I wrote a summary of that other part right down below here. So this, we'll be doing both methods on a lot of these, so you can see. Well, it's important to do both, right? These are both important, and it's also great to see if they agree or not, and sometimes they disagree. So if the null value falls within the confidence interval, that supports the null, and we fail to reject the null, okay? If the null value is outside the confidence interval, that's evidence against the null, and we reject the null. Okay, so use this as you're practicing. And then there's one more little thing I want to talk about in this video. It's almost over, it's kind of a long one. Practical significance versus statistical significance. If you were wondering, why do we care if exactly 1/3 of households have a cat? You're right. Like, what's the point? So this is the idea of statistical significance versus practical significance. And we had a very large sample size, right? So if you have a very large sample size, then even a small, tiny difference can be significant, okay? But that doesn't mean it's meaningful, or it doesn't mean it's practically significant. So do we care if it's 30.4 versus 33.3% of households have a cat? Probably not too much, but it's around 1/3 or a little less than 1/3. Okay, so that's the idea with practical versus statistical significance. So just because it's statistically significant doesn't mean it's practically significant. It doesn't mean we necessarily care, right? So very small differences can be statistically significant if you have a large sample size, okay? So later on, this is beyond the scope of this course. Later on, you might learn how to choose a sample size so that the statistical significance reflects a meaningful or practical difference, okay? And then I just put a note down here, which is what we wrote about the confidence interval, the size of the effect. Confidence intervals should accompany significance tests to estimate the size of an effect or difference, okay? So they not only give us, the hypothesis test gives us the strength of evidence, and then the confidence interval gives us the size of the effect. So even for tests that are left tail or right tail, not two tail, we'll still do both and then see how the methods compare. Okay, great. Thanks for watching, and I'll see you in the next video.